So today we will find electric potential due to a dipole, and we will find electric potential at an axial point. Then we will find electric potential at an equatorial point, and finally we will find electric potential at a general point. So let us start doing all this. Suppose we have a dipole with two charges, minus q and plus q. The length of the dipole is 2L, and the center of dipole is at O. So at L we have to find electric dipole at an axial point P, which is at a distance r from its center. So let us proceed. Since we know that potential is equal to 1 upon 4 pi epsilon naught q upon r. So we will be finding potential at point P due to negative charge minus q of the dipole and due to plus q charge of the dipole at point P. And potential is a scalar quantity, so we simply add the two potentials using algebraic addition of the two potentials. So let us start. Potential due to minus q charge is equal to 1 upon 4 pi epsilon naught minus q upon, and the length is equal to r plus L. Length in between minus q and point P is equal to r up to center plus from center up to the position of minus q, that is L. Okay. So this is potential due to minus charge. Now potential due to plus q charge is equal to same formula, plus q upon, here you have r minus L. So on adding the two, V potential at point P due to the dipole can be given as V is equal to V minus Q plus V plus Q. Algebraic sum. Potential is a scalar quantity, so it is equal to 1 upon 4 pi epsilon naught Q upon R minus L minus 1 upon 4 pi epsilon naught Q upon R plus L. Okay. So let us simplify this equation. So it is equal to Q upon 4 pi epsilon naught, and let us take LCM of the two. So this is equal to R square minus L square, and in numerator it is equal to R plus L minus R minus L. Okay. Therefore potential V is equal to Q upon 4 pi epsilon naught. Here you have R square minus L square, and your R cancels out and it becomes 2L. Therefore potential at an axial point, potential P potential at P along an axial line V is equal to, and here you can see this is dipole moment, charge into product of one charge into distance between the two charges is called dipole moment. So it is equal to 1 upon 4 pi epsilon naught capital P upon, okay, this is your R square minus L square. This is your potential. Suppose the length of the dipole is very small. Dipole used to be very small in length, its length. So if L is very smaller than R, then we can neglect L. So V becomes equal to 1 upon 4 pi epsilon naught P upon R square. So this is one way to represent potential at an axial point. But you can even elaborate it and you can produce it in a form of scalar product. As you have dipole moment is a vector quantity, position vector also is a vector quantity, so it can also be written as scalar product 4 pi epsilon naught P dot R. I have taken one R vector, a vector quantity, position vector quantity. So let me add it in a numerator and denominator too. So here you have R, okay, and here you have R. So when you add the two, you get RQ. So this way you can produce potential in scalar form and in vector form. Dot product of dipole moment vector and position vector. Here P is dipole moment. Now, so this is the potential at an axial point. So let me omit this thing. Okay. Now potential at an equatorial point. Second case, this was your first one. At an axial point. Now, potential at an equatorial point. So let us take a dipole with two charges minus q and plus q, and let us pass an equatorial axis from in between the two charges which is passing through origin O, and we are interested in finding potential at a distance r on this line. So, as before, the length of this dipole is 2L, and distance I have taken. So let me write this distance, this directed distance, and this is equal to under root L square plus R square, and same will be this hypotenuse also. This will be root under L square plus R square. So we have a point over here and we have to find electric potential at this very point. Now, potential V due to minus q charge will be equal to 1 upon 4 pi epsilon naught minus q upon root under L square plus R square, and potential due to plus q charge is equal to 1 upon 4 pi epsilon naught q upon root under L square plus R square. So these are the potentials at point P, and if we do algebraic sum of these two potentials, then we will get net potential at point P. Therefore, net potential at point P, let us assume that this potential is V. So V is equal to V due to negative charge plus V due to positive charge. As potential is a scalar quantity, so algebraic sum, and this is equal to 1 upon 4 pi epsilon naught q upon, so minus q upon under root L square plus R square, and plus 1 upon 4 pi epsilon naught q upon under root L square plus R square. So this is equal to 0. At axial point it is equal to Kp upon R square, and at equatorial point, at every point you have potential 0. So you have potential 0 at this very point, and at every point on this equatorial line you have potential 0. So now potential at a general point due to a dipole. So we will go a simple way. We will not go through a very elaborate way. So let me start. We have a dipole of equal and opposite charges plus q and minus q, and we are interested in finding electric potential at this point P, which is at an angle theta from the dipole. And suppose this distance is r1, distance from this positive charge is r2 up to point P, and the length of the dipole is, as before, it is 2L, and the central point origin we can take as O. Therefore potential V at point P, so therefore P will be as before. As before, it will be V due to negative charge plus V due to positive charge. So let me write, it is equal to 1 upon 4 pi epsilon naught. Okay, this is your minus q upon r1 and plus 1 upon 4 pi epsilon naught q upon r2. So let us simplify this. ये आपका हो जाता है 1 upon 4 pi epsilon naught. Okay, let me take q also outside, and 1 upon r2 minus 1 upon r1. Therefore potential is equal to q upon 4 pi epsilon naught R1 R2, and this is your R1 minus R2. So let us find the value of R1 minus R2 and R1 R2. Let us assume that the dipole is very small. So that this angle theta 1, so theta 1 is nearly equal to theta only. Now let us make one construction in the diagram. Let us draw a perpendicular line here so that it is meeting at 90 degree on line from minus Q to P. Okay. Here you have a right angle triangle in the diagram. If you could see in diagram, we have a right angle triangle. So cos theta 1 which is nearly equal to cos theta, and that is equal to cos theta is base divided by hypotenuse, and this base is equal to, if you see that it is equal to, in diagram, just look here in diagram, it is equal to R1 minus R2. This base is equal to R1 minus R2. So base R1 minus R2 by hypotenuse, and hypotenuse is 2L, length of dipole. Therefore R1 minus R2 is equal to 2L cos theta, and if you also assume that R1 is very nearly equal to R2 and it is very nearly equal to R. Therefore, R1, R2 can be taken as R square. Okay, from these two things, from the value of R1 minus R2 and R1, R2, you can simplify equation 1. Here, let me name this equation 1. So, in equation 1, potential V is equal to 1 upon 4 pi epsilon naught. Okay, let me write Q also here, and 2L cos theta upon R square. Therefore, potential V is equal to, okay, you can write this Q2L as dipole moment P. So it becomes equal to P cos theta upon 4 pi epsilon naught into R square. So this is how you can find potential at different points. So what we see, how the dipole potential changes from potential due to a point charge. We find that there is difference in potential at a point due to a point charge and due to a dipole. Here you can see that in dipole, V is inversely proportional to square of R, and in point charge, V is inversely proportional to R only. So you can define a dipole in yet another way. So definition of dipole, Any charge configuration in which potential varies, potential obviously due to the dipole varies inversely to square of distance. Then such charge configuration can be taken as a dipole. Okay, let me think. So potential due to a dipole at a general point, it comes equal to k p cos theta upon r square. So from here you can see that potential due to a dipole also depends on its polarity, its orientation in fact, because it is depending on cos theta and it is proportional to dipole moment. These three things. It is depending on number one, orientation, 2, inversely proportional to square of distance, and it also depends on dipole moment.